Hello, everyone at home. I think we're ready to roll. Okay, so I'm just going to give you a bit of a background on the End-Permian extinction, give you a bit of a feel for what sort of conditions led to this extinction, and maybe some lessons we can learn from it for the present and possibly the future. So there's a book that came out by Mike Benton called When Life Nearly Died. It pretty much sums up how the extinction went down. It was by far the largest mass extinction in Earth's history, at least the ones that we've detected so far. It included between 50 to 70% of all genera, so every genus that was on the Earth at the time, well, every fossil genus that we know, 50% on land roughly, and 70% in the oceans. And that basically translates into something approaching 9% for the species in the oceans, and nearly 50% of all species on land. So this is yep, sure.
Interrupting. I don't think the people online can see the screen.
Yeah, no, it's sharing.
You know how to fix that? It's oops. Sorry. It's seamless. Yeah. Probably this one. Just screen two, yeah. Sorry about that.
No worries.
Now we can see
There we
it.
go.
Thank you.
Cool. No worries. All right. Okay. So so if you're not too familiar with this mass extinction, there's a couple of good reasons I think that might be responsible for that. I mean, it is the biggest, but there might be some other variables to go on. One is the fact that it's quite old. This is 252 million years ago. And there was a couple of pretty big ones between now and then, including the dino killer, the one that led to the extinction of those non-avian dinosaurs. And related to that is the fact that the dino killer looked a bit like this. And so it makes for some pretty dramatic cinematography and some pretty cheesy movies. Very flashy, very explosive sort of extinction compared to the End-Permian, which is much more of a long, painful dying process. It's sort of like a car crash rather than a cancer. So it's a lot harder to put into a graphical visualization. And also you got some pretty spectacular pictures of pterosaurs with fiery holes in their wings and some sweet Tyrannosaurus silhouettes on a fiery backdrop. You know, it's hard to beat that sort of glamour. There's a couple other reasons why you might not be too familiar with it. One is the survivors were few and far between. So if you think about it, dinosaurs, I mean, we have dinosaurs still. We talk about the end of the dinosaurs, but there's a whole bunch of them still flapping around today. So really, if it was more complete an extinction, you wouldn't even have those guys. So there's many classes and orders of organisms that didn't make.
This is crazy, Marg. It's just not one thing. It's just not freaking working.
Sorry.
It's not mirroring. See?
Sorry.
The voice would be on.
I don't have. Sorry, I hate Zoom.
That's all right.
Oh, fucking hell. I don't know why it's doing that.
Those are hiding for some reason.
Everyone at home, just make sure you're on mute, maybe.
Well, I can mute.
There we go.
All right.
No worries.
About that. I'm going this one. Is it the right one?
Yep. We're good. There we go. Okay, so and as our research has been progressing and we're seeing more and more evidence for what caused this extinction, I suspect that not just because of my own research and all the research going on, but the drivers of this extinction might be becoming more familiar to us in the present. So we'll retouch on that later down in the talk. So these are some staggering numbers. You know, to think about 85% of all marine species is pretty devastating. And so I had a quick search into the pop culture world to see what sort of villain could could rival this sort of devastation. And all of the villains I could come up with, they're all pretty small-time, pathetic losers compared to this. The best one I could find was this guy, Thanos. I don't know if anyone is a Marvel whiz, but so his special power was that he could kill 50% of all, maybe someone can correct 50% of all organisms in the universe or something. But like, if you talk to an ecologist, most species would probably be okay with 50% loss of their species. So you wouldn't have this sort of level of extinction, even with 50% loss of all of the organisms. I mean, you know, forget about the Andromedans, but just on Earth, we'd probably bounce back. We wouldn't have 85% of our ocean species lost. So these guys are all a bunch of losers. They're not thinking hard enough. So we need to think of other culprits that might do the job. So we had a big rock for one of them. That seemed like a pretty good way to wipe out a lot of species. But if you look at, this is the timeline of the extinctions and the sort of the number of genera that went extinct throughout the last 540 million years or so, basically the Phanerozoic. And the big outlier is this one in the middle, this Permian-Triassic spike here. So really what we can start seeing is, okay, we've got a whole bunch of little mini or secondary extinction events, and then you've got these big five, which are the ones that wiped out more than, they estimate somewhere between 50 and 75% of all species. So, and as you'll see, almost all of these are linked to what they call large igneous provinces. These are huge, enormous, I mean, a volcano doesn't give it justice. It's like if we were to say that, you know, the Boxing Day tsunami was a wave, you know, it's like, it's a completely different magnitude of power we're talking about. These, I'll give you some examples of how big these things were, but these are, these large magmatic events have been linked to almost all of the extinctions in the, or mass extinctions in Earth's history. And a few of them, we just haven't got the data to really support that yet. So I'm going to suspect that some of these black arrows here might end up being linked in the future. So and there's a big rock for one of them, as we know. As we get more and more evidence, it looks like the impactor ultimate driver of these extinctions is actually the outlier, and the more likely way to kill off most life on Earth is through this magmatic igneous province. So there's one we're targeting today. So what puts the L in LIP, in large igneous province? So here's an example of one of them. This is the one we're actually focusing on today. This thing is extraordinary. So we're talking magmatically derived rocks, so, you know, igneous. These are not just volcanic, but also intrusive rocks. Several kilometers thick, over hundreds of square kilometers of hundreds of thousands of square kilometers across the Earth's surface. So if you quick maths, you can basically start adding up millions of cubic kilometers of magma in these events. So once again, this is unlike anything we can really point to. You know, this makes, you know, this will make Iceland look like, you know, like a pimple compared to this sort of event. So this is another, this is a reconstruction of what Siberia looked like 252 million years ago. And the Siberian traps is this one up here, as you may suspect, in northern Russia. It's not actually the largest in terms of volume of magma, but it's probably has the highest volume of gases associated with the with this event. So, and we'll go into how that works in a second. So this seems to be a very common pattern in Earth's history, that these large events, these large igneous events occur, and lots of things die from these. But the proximate causes, the things that actually drive the extinction, you know, the magma is one thing. How do we get from magma to biodiversity loss? All those tangled webs of interacting causes is what's actually what most of us are spending most of our time on in the mass extinction field. So what we've got, so when you start putting together the possible causes of extinctions, it starts to look a bit like a bowl of spaghetti with all these interweaving flowchart lines with a nice big molten hot magma Siberian traps sitting on top. So this is the types of drivers. They range from the mundane, you know, the things we're very familiar with, the ones that we have very, very strong evidence for because they're happening today or they've happened in historical past, to the quite exotic ones that we're not too sure if they're even they're big enough to cause damage on a global scale. So then there's also a range of different drivers that are more solid, we have better evidence for, and then there's other drivers that we don't have a whole lot of evidence for, partly because they don't preserve well, but also we just don't know of any historical cases when this has happened. So let's take an example of a fairly solid set of causes from the Siberian traps at the top to the marine mass extinction. So if we crank up the CO2 and we crank up the thermogenic, let's go out of the way so I can see what I'm doing, thermogenic gas emissions, for all intents and purposes, for our purposes tonight, we can treat those more or less as the same thing. There's a subtle difference. CO2 is directly out of the magma chamber, is being pulled out of the ground, whereas the thermogenic gas emissions relates to metamorphism. So if you have a hot rock coming up through the crust, what's it going to cause to degas on the way up? So because of these huge sill-like emplacements of magma, you actually cook the rocks that they're coming up through, and those rocks often have hydrocarbons, they have a lot of carbon in there, and they become part of the problem. So let's just treat them all more or less as greenhouse gas emissions. And we know pretty well what happens when you crank those up. The most direct path to extinction is just pushing species out of their nice tolerance range. If you can just grab a species, crank up the temperature a little bit, they won't like it very long. It's like that analogy of the frog in the hot water. If you just crank up the temperature slowly, it stays in there until it cooks. Another way that's probably less obvious is this way here, is through the path of ocean anoxia. So depleting the amount of dissolved oxygen in the oceans. And this is both of these are in play during the End-Permian extinction. We have some really solid evidence that this is happening in the oceans. I'll give you a bit of an example of that. But with the tentative drivers, pretty much all of the ones related to the continental or the terrestrial extinctions are quite tentative. This is where my research comes in. I'm focusing almost entirely on the land and freshwater systems, and we'll test and look at some of these and see if they can help us out. So going into the oceans first, just to give us a solid idea of how we can kill most ocean life on Earth. If we were to, this is a cross section of an ocean with the continental shelf here on the left side, the ocean on the right, and basically what we're seeing is as you turn up the temperature, the problem with the water, if you make it warmer, is that the oxygen doesn't diffuse as easily when you increase the temperature of the water. So even organisms that like it can survive at pretty low oxygens. They're basically living, or they're dying in no oxygen now. So you raise the level in which that low oxygen level water is coming up to the surface. So this is essentially what they call shallow anoxia. So instead of just being low oxygen at the very bottoms of the oceans, the low oxygen actually comes a lot closer to the surface of the ocean. And on the top, basically you're cooking the top surface, so that now you've got this narrow window of survivable area in the oceans. This sort of Goldilocks, not too hot, not too anoxic conditions. And if there's lots of evidence for this, geochemical, sedimentary, if we run ocean models, you can actually crank up the ocean's temperature and see what happens, and this comes out. And for my particular expertise, this is the angle that I'm really interested in, is looking at the selectivity of the extinctions. So what species survive the extinction can actually give us an idea of what sort of drivers were killing them. So for example, in the fossil world, if you look at ocean organisms, there's a whole range of different types of ecological niches in the oceans. Some are adapted to deep water, some are adapted to the shallowest. Now it turns out that only the ones that survive in this weird little, shelf margin zone survive. So that gives us an idea that most of the shallow ones were dying out, and most of the deeper ones were as well. So you've got this nice little Goldilocks zone of niches that survived. So if we can use the End-Permian extinction as an end member of very extreme warming from mass extinction, from large igneous events, then we should be able to use that to interpret other mass extinctions. And maybe if the drivers are not too exotic, we might even be able to apply some of these lessons to modern warming. So this is a quote from Charles Darwin. Is this a difference of degree or of kind? Is this a fact that maybe it was the End-Permian just an anomaly, it's just a very strange combination of place and time and elements, or is this just the end member of a spectrum of different extinctions? And as I might be able to show you by the end of the lecture today, that we're actually moving towards that sort of model. That this is just an end member of a series of different mass extinctions, and this is just the biggest of the lot. Another good thing about looking at this one is because the signal from the fossil record is so clear, we can use this as a model of what happens when things go really bad. And then we can sort of work our way backwards from there. And so the fossil record is super well preserved, and the extinction rate is very well constrained because it's so dramatic. So for the continental mass extinction, the main two questions I was looking at is refining the timing over long and short-term periods, but most important for this little seminar today is actually looking at the causes, those proximate drivers of extinction in land and freshwater ecosystems. So to get a handle on this, believe it or not, we have some pretty spectacular rocks to look at this stuff. If anyone spent any time near Wollongong or just south of Newcastle, you've got some pretty spectacular outcrops of the End-Permian extinction in action. And we also have a lot of well cores throughout this basin. This is the Sydney Basin, and as the name suggests, Sydney is right in the middle there. And you've got some pretty nice, spectacular Permian-Triassic outcrops. Wherever the blue meets the turquoise, I guess, those are your Permian-Triassic boundary outcrops. Lots and lots of wells as well, like lots of drill cores that have been made in this area for hydrocarbons, mostly coal, but also water. And this is a fairly continuous succession of those changes of the environment across the Permian and Triassic. And this is almost entirely continental. So we're looking at not marine, we're just looking at the deltas, rivers, lakes, that sort of environments. Those are some of the sections we've looked at. We've looked at many more now, and we've even looked into Queensland and some in Tasmania, just to compare. And the preservation of the fossils is particularly good. So we get the whole bunch of well core data, like this thing on the right, lots of outcrop data. And from that, you throw in a lot of different methods. So in here, you've got geochemical approaches, you've got fossil approaches, you've even got some climate modeling going on up here. Most of my emphasis is on the fossil records, so fossil leaves and spores and pollen, so the micro and macro fossils of the leaves, to really give us a handle of what sort of species survived. So the very first conclusions worth throwing in there is we can talk about more of this later if you like, but during question time, but this isn't the emphasis of the talk, is they have a pretty strong evidence for early collapse of the continental ecosystems. So we have a nice, happy, coal-forming plants going along, wetland floras, really super productive. And then all of a sudden, this extinction happens. So in this little column here, you can see coal, very nice. Coal depositional environments here, and then after that, no coals for several million years. Now, this coal gap is one of the main questions that we're trying to tackle. Is okay, the mouse doesn't actually work there. There it is. This coal gap, coal, and then no coals there. So what we're really looking at is these coal-forming plants died off, and then they were not replaced by coal-forming conditions for quite a long time. But the marine extinction happened pretty well constrained over 300,000 years later. So this is a weird mystery, and there's a lot of hypotheses to delve into here. No one's particularly sure why that is, and we're happy to discuss it with you later, but I'm happy to push that off to question time. But it hasn't just been in Eastern Australia. It's also now being confirmed in South Africa and China. So this doesn't seem to be a local phenomenon. It seems to be more of a global thing. And not only that, but it looks like other mass extinctions seem to show a similar pattern where land extinction seems to occur before the oceans. And we're not too sure why that is. So keep watching this, and hopefully I'll have something better for you to say. The next thing to really explore is what the plants themselves are doing. So I mentioned that those coal-forming plants died off, but the actual coal-forming plants, the new ones, the next generation, the millennial version of the coal formers came back in a big way, but they were not forming coal for a long time, for about 7 million years. And that's what we've got to start questioning. Why is it? The conditions just weren't right for some reason. And this is why this is part of the big question I was trying to tackle. And there's a good chance that maybe what happened is, instead of just being a one-off nasty event, things just kept getting progressively worse and worse and worse, which might partly explain why the marine extinction didn't happen for several 100,000 years later. Maybe the conditions need to get so bad before the marine ecosystems could feel it. So this really was at the end of a massive biome, or the end of an era, literally end of a Paleozoic era, but the end of a big ecosystem across the globe. So on a supercontinent-wide scale, we've got an almost near loss or near total loss of the carbon sinks. So the places where you have your carbon being drawn down and being formed into hydrocarbons, like in coal-forming places, or into phytoplankton rich areas, all those primary producers seem to have almost been completely lost or replaced. So these two large algal and land plant provinces were completely wiped clean. So here's a paper I published earlier this year looking at the algae. 2020 was really my year of algae, which I didn't think was going to be the case, but it seemed like a nice slimy year to delve into the world of algae. And what we found is across the Gondwana and the southern part of Pangaea, the algal distributions became a lot more constricted. So you can see here, this is the pre-extinction range, which is quite broad before the extinction. And then all of these fossils, they all show very similar pattern. The post-extinction range is a lot more contracted. And so these, and the fossils themselves tend to be quite uniform in their assemblages. So we thought this is enough to call it a new algal province, which pretty much matches up to the same biogeographic realm as these Thalassopteras, these coal-forming plants, and probably for the same reason, same climatic reasons, same geographic reasons. It seems like there was a very homogeneous ecosystem across this southern part of the planet. And so these guys were basically wiped clean from the face of the earth. Now, I've been saying how nasty this extinction was. It sounds like, the outcrops must be amazing. They must be so good to see. And they're not quite as awesome as you might think. I mean, if you were in a car driving to Sydney from Wollongong, you'd drive over this bridge. And actually, the last time I gave this talk, one of the chaps after the talk said, "Oh, I've driven on that bridge. I didn't know there was a mass extinction under it." I said, "Yeah, no one really does." I'm sure that the guys or girls that wrote the graffiti here didn't realize either. It's a bit of a rude one. Hopefully people can't read that. But so this is not the most, doesn't have the same gravitas as I was hoping the mass extinction in outcrop would have. But you compare that to, say, there it is right there. I'm sort of pointing at the dead zone. I'll talk about that in a second. But if you compare that to how the Chinese mass extinction looks, and they've got like this whole sort of almost like a mass extinction memorial set up and I think my Chinese isn't particularly good, but I think this little poster says here, "Here lies the last trilobite." So, so I think that they're really taking it a bit more seriously than Australians. So if you go to the Coal Cliff section, you have to sort of find the mass extinction amongst the graffiti and the urine stains. Whereas in China, it's a bit more, maybe it's just different national priorities. I don't know. So lest we forget, I think we should set up something similar in Australia for the 90% of species that went extinct or whatever. 85. So in outcrop, if you look a little bit closer, if you start hacking away at those rocks, what you'll see is these coals are made up of one plant, and pretty much one plant alone. It's a single Soptris. I mentioned it before. It's a nice little reconstruction that our resident artist at the museum put together. And then above that, yes, you've got this more than 6 million year, closer to 7 million year coal gap. And this is a global phenomenon. So basically you can look all the way around the world and you won't find coals of that age in that post-extinction world. What the heck was going on? Something nasty. Because the plants that form the coals were there, but they weren't forming coals. So if you look up even closer, we take what we've just described as a new stratigraphic unit called the Fraser Beach member. This little sliver of rock here, this is where a lot of the action is. All right, it's between 50 to 140 centimeters thick, depending on which part of the basin you're looking. The rocks themselves give us a nice clear signal of what environments they were, the lakes, rivers, maybe some deltas thrown in there. Mostly just carbon-rich mudstone, a little bit of sandstone. The duration, because of our pretty well-controlled uranium-lead radioisotopic dates, we can train the age based on those to pretty narrow window. The whole unit of just over a meter thick is less than 100,000 years. And the geochemistry, it shows a pretty crazy signal. These are all things that you won't actually look at. You won't notice if you just look at the rock by itself. And you kind of have to look at it with a series of different approaches, geochemical, sedimentary, fossil stuff. The geomodeling based on the geochemical data that we have shows that we have a CO2 increase of between 4 and 6 times the sort of pre-extinction baseline, which, by the way, is roughly about what we're at the moment, about 430 parts per million, 420. And then the temperature went up to about 10 to 14 degrees increased from the baseline. And the seasonal precipitation is really important, particularly important for those plants. So it went from an ever wet condition to a very, like a seasonal drying sort of conditions. And what sort of fossils might we find? Well, not a whole lot. Maybe because of it's called a dead zone, we don't expect to find too many. In fact, that's not true. We do find some fossils, but they're not quite as spectacular as you might expect. So this is one of the bigger types of fossils we found. There's a whole bunch of vertebrate remains, but not as body fossils, but as trace fossils. So tracks and burrows. So there's some pretty spectacular burrows in the rocks here. Actually, this is the Fraser Beach area, just in northern part of the Sydney Basin. And nice little trackways of something that looks a bit like one of these guys, cynodont. And this is probably what was causing the burrows as well. So there was something living here, leaving marks. And these are what they call estivation burrows. Basically, this is not a hibernation burrow. That's for getting out of the cold. This is actually for getting out of the heat. Okay, so this is probably a good evidence that these things were one of the best ways to survive the ongoing devastation on upstairs, is to get out of the heat for a while, especially over the hot part of the year, and stay in the cooler areas down below. They're pretty small, but they match pretty similar to the sort of burrows you find in other parts of the world, in South Africa, for example. Now, what else do we find? Well, this is our pre-extinction sort of happy coal-forming areas, nice of transpiration by these broadleaf forests. We had fairly low water tables and a lot of precipitation, ever wet conditions. Then the mass extinction happens, and the fossil record goes from full of plant bits of leaves and cuticles and seeds and whatever you like, to pretty much this black stuff. Pretty much every slide you look at, this is transmitted light, so you're looking at a slide with light coming in from behind, and it's just a bunch of black stuff. Okay, well, that's a bit concerning. What looks black on transmitted light is charcoal. So we wanted to confirm that, so we decided to look at transmitted light, reflected light, and see what it looks like from the top down. And it's not all charcoal. You can see charcoal, the shiny stuff here, and you've got some pretty dull stuff, but there's a lot of charcoal here, getting up to 80–90% of the total organic remains of this interval, this lower part of the dead zone, is charcoal. So lots of fires going on for some strange reason, maybe not so strange. After that, we actually have, rising from that charcoal-rich area, we have a series of disaster species, and they're not just occurring all at once. They tend to occur in very short bursts, one after the other. So we already talked about these guys, and these disaster species are good indicators for something that's completely out of whack. The ecosystem is not in a sort of it's not in equilibrium. These are things that are taking over in a big way. They're basically like the pests or the they have out of control sort of reproduction and productivity. But things like this, these are saprotrophic fungi. These are fungi that grow on dead things. You can find them quite commonly when you go to a freshly charred area. You also see things like this. These are fern spores, and not just any fern spores, but these are the ferns that were living at the time before the extinction, but in the understory. These are the sort of the underdogs of the Permian, and then they blew out into pretty huge populations after the extinction. Also, lots of bacteria and green algae. We'll come back to that. And so we're really seeing like this sort of disturbed ecosystem going on here. Lots of these sort of miserable, sort of pathetic animals that you and plants and fungi. Things that you probably would. It's a bit harsh to say that, but I sort of call this as an assemblage of cowards, like this guy, and underdogs like these ferns, the scum suckers like the fungi, and the low life slime bags. Now let's talk a little bit about that slime. So this is what it looks like. It looks pretty slimy. It's not particularly nice to look at. And you would think, oh, well, amorphous organic matter. What the hell can we tell from that? Well, without morph, you can't really tell what it was. And not until you stick it under ultraviolet light or ultraviolet fluorescence, and you can start seeing it start to glow pretty strongly. This is pretty much the same signal you'd get from cyanobacteria in modern bacterial colonies. You can also look at the geochemical signal, and this is a pretty strong evidence for bacterial derived blobs in our organically preserved slides. And then you've got these algae that I mentioned before, mostly green algae, and these are particularly important because these types of algae, these chlorophytes, they have this nice desiccation resistant wall, which allows them to be preserved for a long time. So that's why we can find them. But also they lay in the soils and can resist a lot of desiccation. They can resist being dried out seasonally. And then when the water tables rise again, they flourish and they basically become algal blooms. So these, it's not just within this particular dead zone. We actually find dead zones in the modern world where these guys take over in disturbed environments, particularly where you have very warm water combined with high CO2 and lots and lots of nutrients introduced. So these are fairly common in areas of disturbed environments today. So if you look at the fossil record, we're going back to the fossil record and see how that timeline matches up. We've got those glossopterids here that basically peter out at the mass extinction. We've got those other plants that come in afterwards. They're the coal formers of the Triassic, but they're not forming coal. And the pollen record of those guys is pretty much matches that. So this black part of the pollen record is stuff produced by those coal formers. There are some that trail on up here, but they're being produced by things that are not they're not glossopterids. They're actually closely related plants. And then you've got these other things that come in. And then if you look at the slime record, the algae and the bacterial record, their abundances go through the roof. So you've got basically hovering around 0 for the samples before the extinction. And then when you get to the extinction, they go up to 60, 80% of the assemblages in some samples. And if you can focus on this little dotted line just for a second, this is actually what's particularly important. This is the concentration. It's not just total abundance. It's not just the proportion of fossils of algae compared to other fossils. It's actually how much per gram of sediment we're talking about. Now, this sort of concentration is pretty high. I'll get to that in a second. So this is what I call the 3 million year slime dynasty. And when I put in a search in Google for Slime King, it came up with this thing. I knew there would have to be something. And this just sort of confirms the fact that if you look for anything on the internet, you'll find it. It turns out this is a character in some Japanese video game. I don't know what it is, but I'm sure that if I'd gone scratching this over a little bit further, I'd probably find a pornographic version of the same thing. That's another truism of the internet. So let's just move right along. But so these sort of concentrations really are getting up to that sort of toxic level of concentrations. These are sort of the concentrations you'll find in these bloom events in freshwater and inland seas. So these are things that can kill off your animals, because it sounds a bit counterintuitive, but when these algae and bacteria go through the roof in terms of their abundances, they actually decrease the available oxygen in the water. Sounds a bit, hang on, that's weird. They're photosynthetic. Why aren't they producing oxygen? Well, it's because when they die, they actually bring a lot of the oxygen with them. So when they have these flourishing events, they go into huge bloom proportions, but then they take a lot of the oxygen with them when they die. So they actually get buried with their oxygen. And that becomes a real problem for organisms living in the water. And not only that, but the cyanobacteria and other types of blooming microorganisms actually have metabolic byproducts that are toxic. And so if you have a lot of these things, they'll become pretty bad for your ecosystem. So this could be, and the fact that they're reaching such bloom proportions is a good indicator that these were probably causing a big chunk of the extinction, or at least a lot of the biodiversity loss in the freshwater systems in the early post-extinction phase. Not only that, but the fact that they were coming in for several thousands, hundred thousands of years probably made sure that those ecosystems couldn't recover for quite a while. So here's our sort of building up a model here based on the fossils, the geochemistry, the ages, all that sort of stuff. Happy plants forming coals beforehand, lots of moderate temperature, CO2 is pretty much where it is today, and high precipitation, consistent, ever wet conditions. you have this extinction event, rapid warming and change of your climatic signal to a more seasonal conditions. What happens in there? Well, as we can see in some parts of the world, fires tend to go up in these conditions. This may have caused, or in conjunction with the heating, may have caused the deforestation, which we know happened because basically you have no trees left. There's no soils with trees anymore for quite a long time. The evapotranspiration goes down, so the plants are no longer taking the water out of the groundwater, out of the water table and putting it in the air. Instead, they're actually, the groundwater is just rising. And so you end up with these ponding events. And a lot of that, without those roots to stabilize the soils and that rising sea level, rising water level, essentially you end up with a lot of nutrient influx into that, into those fresh water bodies. The water tables rise, the soils come up, and this is pretty much enough to cause those microbial blooms. I mentioned also the other two things that you need for microbial blooms is warm temperatures and lots of CO2, and we knew that was happening as well in a big way. So this wasn't just happening in the short time after the extinction, but actually for a couple of million years after, we had temporary algal bloom events, not quite as extreme as the early phase, but they kept persisting for quite a long time. And not until you hit basically another mass extinction event, which is called the Smithian-Spathian event, which ended up cooling the world, that you end up getting back to something approaching normal temperatures. This is there's a good chance that this isn't very well defined, this extinction. So we're not too sure what caused it, but it may just be that this is how long the Siberian traps were erupting for. We know they were erupting for at least 2 million years. It could be 3. So if that's the case, then this could just be when they ended and things started going back to normal by themselves. So lots of CO2, lots of other greenhouse gases being pumped out continually for 3 million years, and this is what you get. Possibly, this is with our current model. Now, not just that, not just for the mass extinction. Now we can take this model and apply it to other intervals. So this is a timeline of those other extinction events that we talked about. Now, these little triangles here, those are our large igneous province linked events. Oops, sorry. These guys here. Now, lots and lots of them scattered around here. You've got this one here, which I also mentioned is the End-Cretaceous, the dino killer. There's a big chunk of volcanic or igneous rocks there as well, but it hasn't actually been shown that that was the death knell. It looks like the big rock was what took out the consensus is really converging on that, that the rock was really what knocked them down. If the large igneous province set them up, the rock knocked them down. And if you start looking at the microbial records, the marine records are pretty well established. Almost all of these igneous province events are linked to algal bloom, algal, microbial, and bacterial blooms, I should say. You'll notice in the continental, if you focus on the top row, essentially there's not a whole lot known. There's a lot of these asterisks, and they're just showing that we either haven't looked or we can't look because the rocks aren't preserved. But with this model, we're basically making a big prediction here that you should find this sort of stuff. If this is all hyperthermal driven and the End-Permian extinction is just the end member of these sort of extinction events, you should find these things co-occur. And where the light is good, you do find it. But at the End-Triassic, we have some evidence of algal blooms. And suspiciously, look at that, there's a bit of a gap there in Cretaceous. So it's not from lack of looking. We've actually looked and can't find it there. So it's a good chance that this is another indication that the hypothermal event wasn't what really caused the mass extinction during the Cretaceous. But there's still a little bit of algal bloom in the marine records, so there's enough evidence for something going on there. Yes, so lots of data to be filled in, but we've got a model here to test. Now, if you're interested in sort of longer time perspectives, as if this wasn't long enough, what really looks like these fossil assemblages start reminding me of something really old. So the End-Permian fossil records look a bit like this. You've got microbial mats, you've got stromatolites forming, and you've got these very simple looking algal fossils. These actually look pretty damn similar to the oldest known freshwater ecosystems that we have evidence for. This is 1.1 billion years old, not 2.5, 250 million. So we're really talking about a chance for these microbial organisms to come back in a big way. It's sort of like they knock down all of the grazers and all of these, these animals that are taking over their niches, and they're coming back. It's a bit retro, but they've got their chances for really shine. And even the fossils look the bloody same. This genus is the same thing. It's actually called the same thing. Anyway, but it's actually probably the longest ranging genus in the fossil record. But it's almost certainly not closely related because it's just a small little bag, a little watery bag. You can't really say much about that until you do some other analyses like chemical stuff. So I've highlighted the Holocene here because it may, if some of these things start to sound familiar, you're not alone. Warming plus deforestation plus wildfires in wetlands, particularly carbon sink wetlands. If anyone was watching the news for the last year, you might recognize some of these things, like in the Pantanal wetlands of Brazil. There are some pretty spectacular fires going on there, and particularly last year. And this is a terrible joke for a terrible thing, but this kind of looks like a hot Brazilian wax going on here. Pretty nasty devastation, and unfortunately, what's ended up happening is the conditions in this area are becoming more seasonal, partly because of the changing of the forest cover there, but also because of the warming temperatures. We're having fires much more common in these wetlands than ever before. And who'd have thought? Microbial blooms are going off in a pretty big way. So this is, it's not without modern analogues. And if this is true, if this model holds up pretty well, then we might be able to cut through some of these more exotic drivers of extinction and use the ones that we're most familiar with, the ones that the atmospheric scientists have been banging on about for 125 years, since Svante Arrhenius, one of my Swedish adoptees. He was talking about carbonic acid as a driver of warming and cooling. So basically CO2 could be enough to explain this stuff. And we have enough evidence to say that it can do this in the modern world, but maybe it could be enough to cause nasty extinctions in the very, very nastiest of extinctions. So let's just take this individual little model. Let's take a slice of how this might work, just in the continental arena. So we're looking at land mass extinctions on the left and freshwater mass extinctions. Let's just crank up the greenhouse gas emissions here and see what happens. Well, you end up with warmer, definitely, and in some parts, a drying actually going on. The warming in itself can cause extinctions of fresh and land biotas because of pushing things out of their tolerance range for certain temperatures. But then you've also got the link between fires. You've got the temperature and CO2 emissions that promote the toxic algal blooms and microbial blooms. The fires lead to deforestation. It's this nasty cascade of potential causes here. There's still room for exotic factors, even with this model. And given our present status, I'm kind of hoping that some of these exotic factors can explain the mass extinction of the End-Permian. I'll show you why it is. So if we take this greenhouse gas model as the paramount driver for all these mass extinctions on the continents, then we can start using, basically the motto of the paleoclimatologists. If we look to the past, we can link that to the present by atmospheric modeling and climate modeling projected into the future. This is essentially what the Intergovernmental Panel on Climate Change has been doing. They look at the paleoclimate records, they go back to the ice cores, they look at even more recent records, and they get an idea of how climates are changing in the background. If you crank up the CO2, with rising CO2, as we see today, basically what that means is you need to go back further and further in time until you find an interval with a similar CO2 to today. So when I was born, I was in 1980 something-ish. You guys don't have to know. It's essentially, we're talking 340 roughly parts per million. We're up to 420 when I last checked. Okay, so over that time frame, in order to find another interval when you had parts per million of 340, you had to go back to the deepest ice cores that we had at the time. Now you have to go back 15 to 18 million years before you find a time with the CO2 levels of today. So we really have to go back further and further. And if you take the mass extinction recipe, basically all you need is a lot of change in a small amount of time. And if you change the CO2, ooh, that's weird. Okay, that's fine. I don't mind. Everyone's a critic, aren't they? Jeez. I don't like this part. I don't like this part. Okay. So basically, what we go from the End-Permian is more or less modern CO2 levels to 16 to 22 parts per million, 2200 parts per million. the IPCC, the Intergovernmental Panel on Climate Change, sees roughly those sort of concentrations with business as usual projections by the year 2200. So, you know, and the fact that the curve is going up in a fairly consistent way and without any real take charge measures, there's no reason to think that it won't keep going up. If you think about the Miocene, we talked about that was the last time that the CO2 was this high. What happened there with the biota? Well, there was no mass extinction because the animals and plants had plenty of time to adapt. The End-Permian extinction, the change from nice flourishing coal-forming plants to the dead zone was less than 10,000 years, and that less than 10,000 years is more or less just the fact that we haven't got better precision on our dating. It could be much less than that. And that was enough to cause 45 to 85% of all species to go extinct. And we're seeing that this sort of change to EPE levels within the next, couple hundred years. Okay, so the time frame is shorter than we might feel comfortable. So this is a fairly interesting quote I might raise with you. I'll just read it in full because it's pretty interesting. The increasing evidence that the End-Permian extinction was precipitated by rapid release of CO2 in Earth's atmosphere is a valuable reminder that the best and most sobering analogues for our near future may lie deeper in Earth's past. And as I mentioned, the relevance of these mass extinctions seem to be getting more relevant, not less relevant every year. So this is a pretty interesting quote. Have you guys ever heard of this one? Larry Niven, he's a science fiction writer. Basically, this is my little silver lining here I'd like to leave with you, is that the reason why the dinosaurs went extinct is because they didn't have a space program. If you guys remember this thing, if his idea was if they could just think their way out of the problem, then maybe they'd be okay. If they had some way to get off the planet before this rocket, or even deflect it before it came, then maybe they'd be here today. A similar thing could be said for the trilobites. If the trilobites had some sort of way to capture carbon, might be around today, but then we probably wouldn't be. So okay. So once again, given our present world, I'm kind of hoping for the exotic factors, and unfortunately, the evidence is not really moving in that direction as well as we might like. All right, so some big questions left over. I'll just leave you with this. A couple of big hypotheses. We're in a unique place in Australia to actually look at how the extinction occurred over a wide range of latitudes. So we're looking at, if we just look at these three basins, the Bowen Basin in Queensland, Sydney Basin, and then Tasmania Basin, we're covering about 2,500 kilometers of latitude there. And this is more or less the same sort of spread of latitude during the End-Permian. So what we could see if the species had survived better at higher or lower latitudes. The idea is, and this is a fairly new idea, is that the species at the high latitudes probably fared better. So we can test that in Australia. We can also test whether the plants have some sort of tolerance ranges that they couldn't go past before they went extinct. So was there something that the Calliopters couldn't handle? Was it the temperature? Was it the frequency? We can actually look into this. And Australia is the best place to do that. The selectivity, this is my favorite, because this really will look at the fossils themselves and really narrow down those drivers. The reason is because survivors will be adapted to those changes. The ones that went extinct won't be. So we expect to see fire, but also low nutrient adapted plants. And what sort of algal and bacterial blooms do we see? Are they the same ones that we see in the End-Permian? Are they the same all the way through geologic time? Are they the same ones that we're seeing today? And I'm kind of hoping that I might be able to explain some of these things here in Adelaide. I've been starting getting a bit comfy over the last year and a half, you may have noticed. I figured, why not? I don't know when the hell things are going to change. So if the gods of funding smile upon me, I'll hopefully be answering some of these questions here, maybe with some of the folks in the room. I tried to apply for some money last year. I don't know why. I mean, this is the name of the project. So I don't really understand why they ask. I can't understand them. It doesn't make any sense. So I think it's just luck. So thanks for listening, folks. And thanks for your wonderful sports. Thanks for inviting me down here. And if you have any questions, please don't hesitate to ask me. And there's some papers that we've been published in the last couple of years if you're really interested in this sort of stuff. Thank you very much.